right, on the last set of notes, or the last video, we talked about the models for uninhibited exponential growth and decay. And remember, the equation for that was QT, which stands for quantity at times t, Q of t, equals Q naught e raised to the k times time, right? Q naught was our initial quantity. E is because it grows exponentially at a rate proportional to its size, and we talked about this last time. And so these are going to be applications where we're going to use this equation, so you're going to have to know it, set up these applications. And then what we're going to do is we're going to be finding values. Often we have to set it up, we either have to find k or time. And we're given usually some type of doubling time or half-life are the common ones, and those are going to be the applications that we're going to do primarily, but they would extend to other ones if you wanted to look at, tripling times and other stuff. You should see kind of a pattern when we do these problems. Alright, so we're going to do examples of exponential decay and exponential growth. So we'll start with exponential growth. Alright, so the first example here is on bacteria, growth of bacteria. The number of bacteria present in a culture doubles every 3.5 hours. Alright, so that's giving me a doubling time, which remember we talked about on the last set of notes. When things double at a certain time period, or triple, or divide by half, that means exponential growth. It's growing at a rate proportional to its size. Right, so it means this equation. Right, we start with approximately 2,000 bacteria. Right, so at time 0, that's how many bacteria they expect to have been there. Again, these would be like bacteria cells, and then they notice how big it's growing over certain time periods, and then observe. Alright, we started out with 2,000. 3.5 hours, it doubled to 4,000. Right, we want to find the growth constant, round it to 3 decimal places, find the equation that models the exponential growth with respect to hours, and then sketch a graph. And I'll talk about the sketch when we get there. Alright, so first, K. Right, well, we want to find K and the model. Alright, so we know we're given the initial amount, right, 2,000. Again, I'm assuming this means 2,000 cells, bacteria cells. So 2,000 bacteria cells present. Alright, we know that in 3.5 hours, that will double, right? When I have 3.5 hours into this, I'll double that to 4,000. Alright, to find K, that's the information I'm going to use, right, in order to find K. There's 2 ways to do it. You can either set up the equation and solve for K, plug in your time, plug in your 4,000 and solve for K, or you can remember that simple equation I derived in the last set of notes, where K is equal to the natural log of 2 over the doubling time. And it's the natural log of 2 because we're given a doubling time. If it was a tripling time, it would be natural log of 3. If it was a half-life, it'll be a natural log of 1/2, which we'll get to examples of half-life in a second. Alright, then we'll plug that into the calculator and round however many decimal places they ask us to round. Make sure you round to the places they ask you to. If you don't follow those directions, your answers will be different than the answers that we're looking for. They'll be rounding errors. Alright, and they can be significant in exponential growth. Alright, that's one way. Excuse me, I yawn. Pardon my yawn. Alright, the other way is to solve the equation. If you forget this, again, that we talked about last time, you could solve this equation, which means you could take your general equation, take 4,000, set it equal to the initial amount, e raised to the k times the time it took me to get there, which was 3.5 hours, so k times 3.5, and solve for k. So you divide out the 2,000, you'd get 2 equals e times the k times 3.5 hours, solve, and then we're going to get here, right? Actually, we're going to get there and then there, because you're going to have the natural log of 2 on one side equals k times your half-life, or doubling time, not half-life. And then we divide out and get the same answer we found before. So either one of those methods are fine. Use the one you remember, right? Use the one that's the one that you're going to remember the best. Alright, so my equation would be Q of t equals my initial amount where we started, which was 2,000, e raised to that constant I just found, 1.98 times any time. And so there's the equation that models the exponential growth with respect to t hours. Meaning I can find however big my bacterial colony is, after any hour I want to plug into this. So 5 hours, 10 hours, 20 hours, so on. And we'll solve with it later. Alright, now the simple sketch. Alright, and it's just a sketch. Sketch means you don't have to go into great detail. Remember, we talked about this in the last set of notes, that domain is positive because time is positive, and so we'll only ever sketch these in the first quadrant. And so what we're looking for in your sketch is, first of all, that you're sketching it only in the first quadrant. Second of all is that you label what your axes mean. So this is time in hours, right? That's how fast it's growing in hours. And then this y-axis represents bacteria. Right, so label your axes. And then always start at 0 and always label where we're starting. And I'm just going to mark it off. I'm going to just go here because I know I'm going to grow. So I'm going to mark it off fairly low. And so we're starting down here at 2,000 bacteria. And then we're going to grow. Now, how fast it's growing has to do with that K. The K means, what this means is it's actually growing at 19.8% per hour. Right, that's what it means. That's how fast it's growing. It's the relative percent growth rate. And so this particular bacteria grows pretty fast. It's almost 20% per hour. And so based on that, I'm going to draw it fairly steep. I'm going to kind of curve it up here fairly quick. It's going to take off and grow really fast exponentially. Alright, so that's a fast rate of growth. And that's as much detail as you ever need to show on these types of graphs. Just label what your axes represent. Hours, bacteria. Always graph it only in the first quadrant. We're going to start at time 0. And so make sure you label how much we start off with. And then it should be a exponential curve, which means it should curve up. How steep is subjective. Alright, it's just, again, I drew it fairly steep because I know 20% is fairly high. But if you didn't draw it quite that steep or steeper, again, not the end of the world. It would be fine as long as it looks like exponential growth. How steep it looks is actually how bigger your window is. The bigger your window is, the steeper it'll get. Right, the further down the line you are. Alright, now we're going to be using it. So we found it. Alright, so I'm going to write it down, the equation we found. Too many ones in there. And now we'll use this equation. So it's important that you can find it, right? I can't do the rest of the problem until I do the algebra, right? The first part's algebra. Hopefully, somewhere in your algebra, science, history, they've talked about these before. And this is just a review on how to set it up. Alright, so once we get it set up, then we'll use it. Alright, and the first couple of examples are actually just algebra examples, and then it'll be the last two parts where the calculus will be involved. Alright, so part B. How many bacteria in 24 hours? So let's just take our bacteria equation and plug in 24. So again, just make sure you're careful when you plug that value in. And I don't know why I wrote 25. Should be 24, right? 24 hours. So when you go to type it in the calculator, type in 24 into the calculator. And then it didn't tell us how to round, but just be logical. Like dollars, money, we usually round to the penny. We're talking bacteria. We don't want a fraction of a cell, right? Bacteria cell. So I'm going to round to the whole number, because it just makes sense to do that. And this one's going to be a fairly large number. 24 hours is fairly far down the line. So when we plug it in, I get 231,631. Again, it's approximate. Don't forget units. Alright, remember, applications. You don't want to lose points for not including the, that big number isn't just a number, it's a number with context. So make sure you include the context. Answer the question, right? How many bacteria? Well, that's how many bacteria. Alright, the second one. When will? When will is looking for time. How long? Alright, time. It takes the culture to reach 1 million bacteria. So I know to know at what time, right? How far along the line will it take to grow to 1 million? My population to get to 1 million. So it means I'm going to take my equation for bacteria and set it equal to 1 million and solve for time. Alright, so my equation was 2,000 e raised to the k times time equals my goal of 1 million. Alright, and then solve like we've done in the previous examples. Isolate e, take the natural log to get down to t, and go from there. Alright, so first thing, when we divide out the 2,000, now this fraction, remember, we're never round, but this one actually simplifies nicely. It's going to simplify just to, when I take 1,000,000 divided by 2,000, it simplifies to 500. And this side's my E term. And then I take the natural log of both sides. Alright, so I'm going to be left with the 0.198 times time equals the natural log of 500. Alright, I'm going to go here. And then divide by the k. Right, and then round again. Time, you can have fraction, right? I can have a half a minute or half an hour or whatever. My rule of thumb with time is 2 to 3 decimal places. All right, or round, if it looks like it rounds naturally to something, round naturally to it. So time fractions or decimals are okay. So it's 31.39, and then units, right? Hours, not days, minutes, it's hours. So make sure always include units. Don't forget your units. That 31 means hours. So you need to tell us that. Your answer, that's when-will. It's not minutes, seconds, days, weeks. It's hours. All right, those are algebra questions. So the first calculus question. All right, so our first calc question. At what rate is the culture changing in the 10th hour? And so I know it's a calc question because it's asking for a rate of change of speed. Right? Speed means I need my derivative. Right? In order to find my speed, how fast. All right? And then 10 is when I'm specifically asking, I can find any speed at any time. I want to know what the speed is at 10 hours. All right, so at what rate means find my derivative, and then plug whatever value they're asking me to plug into it. All right, well, the derivative for exponentials are pretty straightforward. All right, first thing you do is write the original exponential, right? The chain rule. The derivative of the e term is first the e term. So write the e term exactly the same. So the 2,000 e to the 0.198 times time. But then you can't forget, you're not done yet, right? It's the derivative of the outside times the derivative of the inside. And so the derivative of the inside is just the 0.198 times time, right, times t. And so the derivative of t is 1. And so you're always going to be left with the k. And that's the way these work. It should make sense. That's how fast it's growing. That's what that growth constant means. That's the percent at which it's growing by. This would be its size. And so it's growing by 20%. All right, little 0.198%. But again, it's growing at this percent, and so it should make sense that my equation is multiplied by the rate at which it's growing. And I'll simplify that. I'll take my 0.198 times my 2,000 just to make it a little easier to work with. And so it's going to come out to a nice number, actually, 396 e to the 0.198 times time. So there's my derivative. And now I'm going to plug my 10 into it. So I'm going to take my derivative, plug 10 into it. Keep wanting to do 8,9 instead of 9,8. 0.198 times 10. All right, and then again, I'm going to round to a whole bacteria. And so when we plug that into the calculator, it comes out 2,868 if I round to the whole number. Again, 2,868 has meaning. It should answer the question. So answer the question. The culture is growing, right? It's increasing, growing at a rate, at a speed of 2,868 bacteria per hour, right? That's its rate of increase, right? Like when you travel down the road, you're going at a velocity, a rate of change in speed, miles per hour. Well, this bacteria colony is growing at a speed, right, of 2,868 bacteria per hour in the 10th hour, right, in this hour. If I picked a different answer, I'd get a different speed, but that's how fast it's growing in that hour. All right, the last one for this problem, I still need my derivative, so I'm going to leave it up there. All right, at what time? So we're looking for a time. All right, is the culture changing at a rate? There's my units, bacteria per hour, so that kind of tells you what the previous answer's unit should be. Rate of 990 bacteria per hour. So we're looking for when is the culture's speed 990 bacteria per hour. What's its rate of change, right? So I need my derivative, and I want to actually find this time when it's equal to the 990 bacteria per hour speed. All right, and I'm going to solve for my time. So I'm going to take my derivative and set it equal to that rate of change. So 396 e to the 0.198 times time, set equal to the speed I'm interested in, which is the 990. And then from there, it's solve it just like we've done now many times. Divide by the first term. All right, now that fraction probably does reduce. All right, but I don't feel like whipping out my calculator and reduce it, so I'm just going to leave it. So e to that k times time is equal to that fraction. All right, next step, take the natural log of both sides, and so now I've got 0.198 times time equals the natural log of that fraction, so of the 990 divided by 396. Again, I'm just going to leave the fraction exactly. We don't want to round, and if you want to simplify, if you want to do that on your calculator, you can. All right, last thing, divide by your k. And so time is going to be equal to, when you plug this in, and make sure you're careful plugging it in, it's the natural log of that fraction first. So natural log of the 990 divided by 396, right, in parentheses. And then that whole thing divided by the k, the 0.198. And when you do, I'm going to round time again, a couple decimal places. So 4.63, don't leave the answer, 4.63. Hours, right? The time has context. It's not days, it's not minutes, it's not seconds. It's hours. So include the units. Don't lose points on homework and test for not including units, because you will, right? You will lose points for not putting it in terms of the application, for not answering the question, right? At what time? Well, if you say at what time, if you say 4.63, well, what is the 4.63? Is it minutes, days, weeks, years? Right? Again, units. All right, problem number 2. We're looking at a mosquito population, which we don't like mosquitoes, and so we're going to use an insecticide to kill off the mosquitoes. All right, so the mosquito insecticide works exponentially, so the population is going to decline exponentially. It was estimated the population was about 12,000 when they started out. So again, it's an estimate just based on size and what they guess is happening. This problem is, so they're guessing about 12,000 mosquitoes were at this particular location when they sprayed the insecticide. They also estimate that it works in 24 hours. Half of the population will have died. So that's my half-life, right? Start out with 12,000, 24 hours later, I should be half that. So I should be down to 6,000. And that's the information I'm going to use to find the equation that models the mosquito decline of the mosquito population in T hours. Round the growth, 5 decimal places. And round it 5 decimal places. If you round it less than that, your answer will come out off. And sometimes with exponentials, it can be way off. So if they say round 2 places, round 2 places. If they say round 5 places, round 5 places. And then we'll get to the sketch like before. Alright, so we know, and I'm going to use m this time. I'm going to be a little more creative. I'm going to use m of t represents my mosquito population. M naught is how much we started out with. E raised to the k times time. Alright, so I know how much I started out with. My initial value was 12,000. Alright, I was given a half-life, right? Half the population. So that means mosquito population in 24 hours is half of what I started with, so 6,000. That was a given information, and that's what I'm going to use to find k. There's 2 ways to do that, and we talked about this in the last video. Either you can remember that simple quick equation, k is equal to the natural log of 1/2 over the half-life, all right? And then plug it in the calculator from there. Or you can use this. If you forget this quick little equation, you can always set it up. Take 6,000 equals to our equation with our 12,000 in our initial value, e raised to the k times the time it took us to get there, right? It took 24 hours to get to 6,000, half of what we started with. And then you could solve that. And if you do, it should solve and simplify down to this. Again, you would divide by the 12,000, that's where you get the half, right? 6,000 divided by 12,000 would give you a half. E raised to the k times 24, then you take your natural log, and there you get natural log of 1/2 equals k times 24. And then divide by 24 and you've got k. Alright, so our k should come out negative since it's declining, and it does, and then I've got to make sure I round to the appropriate space, so 0, 2, and then 3/8, if I round 5 decimal places. Alright, so there's my k rounded to the 5 decimal places they asked me to round it to. Alright, so now my equation, right? They asked me for the equation, I make sure I write it down. The equation is 12,000 e raised to that negative 0.2888 times time. That'll give me the mosquito population after T hours after we've sprayed the insecticide. So I can plug in any time and find out the estimate mosquito population size based on this model. Alright, now the sketch. Again, sketch doesn't have to be in big detail like before. The biggest thing is only graph it in the first quadrant. I can't have negative time or negative mosquitoes. Label your axes. So this is hours. Right, time is in hours, so that's the t-axis. This is the mosquitoes, right? So this axis is labeled mosquitoes. Alright, that's the axis. And then label, I'm going to mark off. And this time I'm going to mark high, because we start off with 12,000 and then we're going to lose. Alright, they're going to die off. So 12,000 I'm going to mark high on my axes because I know it's going to decline. It's going to go down and approach 0. Alright, so the decay rates, it's decaying at about 3%, right? 2.88% is about 3%. So that's not real fast. So I'm not going to come down here really fast. I'm going to kind of give it a slight angle, and then we're going to approach it. Again, there should be a curve to it, but it's not going to come down really steep really fast. And that's where it's subjective. But as long as you've labeled your axes, labeled your initial value, and it's got some curve where it's approaching the t-axis, but remember, it never crosses it. Should just approach that axis. And that's as detailed as the sketches you would ever need to give on this particular type of application. Alright, now we're going to be using our equation. So I'm going to write it down. Alright, so how many mosquitoes? Let's just take our mosquito problem or function and plug 2 into it. So take 2 and plug it into the times bar of our equation. So E, again, be careful with this one because our K is such a big number. Again, no fraction of mosquitoes. I don't want a 0.6 of a mosquito, right? So I'm going to round to the whole mosquito. Right, should come out to 11,327. Remember that 11,327 is not just a number. It's how many mosquitoes we think there is. Alright, so we think there's around 11,327 mosquitoes in 2 hours. So not a big decline in 2 hours, but our percent's not real big, right? It's only 0.0288. And so we're losing. They are dying off. They're just not dying off really super fast yet. Alright, the next question. How fast is the mosquito population declining? How fast? So we're looking for a speed, the rate of change. So we want the derivative, right? Derivative tells me how fast, the speed. They're dying off, right? Declining in 2 hours. So I'm going to take my derivative and plug 2 into it. So I'm going to look up here, right? Take the derivative of that. Remember, it's the same equation, so write down verbatim 12,000 e to that fun k. And then multiply by the derivative of the inside, and it's always going to be multiplied by the k. When these simple applications of exponential growth, uninhibited exponential growth and decay, oops, no t, take away the t. Alright, it's just my original equation times my growth constant, or decay constant, alright, the negative 0.0288. Alright, I will simplify it just because, again, it's a little easier to work with when I plug it into the calculator. Alright, I can multiply that out. It comes out to, when I multiply it, negative 346.56 should be negative, right? E to the negative 0.0288 times 2 when I plug it in. Alright, again, round the whole mosquito. So negative 327 when I plug it all into my calculator. Alright, so when you plug that into your calculator, it should come out when I round negative 3.27. It's not your final answer. Answer the question, right? Answer the question, provide units. And so they're asking how fast is the population declining. Alright, so the population is declining at a rate of 327 mosquitoes per hour. Right, per hour. That's how fast they're dying off. So 2 hours after they sprayed the insecticide, the population was declining at a speed of 327 mosquitoes per hour. Alright, the last one for this particular set of notes. Alright, it's another decay example. Right, a drug decays exponentially in the bloodstream, has a half-life of 6 hours. You start off with 100 milligrams of the drug. At time 0, find the following. And so this is a lot of times how we'll ask the question. Make sure you label with appropriate units. Give your final solutions in the spanks provided. Alright, so on tests, homework, quizzes, whatever. Again, always do that. Always provide units and give your answers in those spaces provided. Alright, so I'm going to write down my general exponential equation. Alright, because we're going to be finding it. Find the decay constant. Round 4 decimal places. So make sure I round 4 decimal places. Give the exponential function q of t. That finds the amount of the drug in milligrams left t hours after you've taken it. So again, it's just finding this equation with all of the parts. The q naught and the k. And q naught's given. I start off with 100 milligrams. Right? They give us a half-life, right? We know after 6 hours, so in 6 hours, so quantity of 6, right, q of 6, I'm going to decay down to half of what I started with. So I'll only have 50 milligrams in 6 hours. So there's 2 ways to find k. Either you use that simple, k is equal to the natural log of 1/2, because it's a half-life, divided by the time it takes me to get there, which is 6, and then round the appropriate units. And so if you do that, it should come out negative, because it's declining. 0.1155. If you forget that, again, you can use this. I know in 6 hours I should have 50 milligrams. So take my equation, set it equal to 50, and plug in the time 6 hours. If you simplify this, it should simplify. If you solve this for k, it should solve down to, because I'll divide by my 100 and there's my half. I'll take the natural log of both sides, so there's my natural log of a half. And then I'll have, natural log of 1/2 equals k times 6, and then I'll get that same expression I had before. Alright, there's the k. Now write again, it asks for the equation, give the equation. So the equation is this equation with the parts that I found, kind of like when we find an equation of a line. You write your slope and your y-intercept in that you find. Same thing here. When I'm finding exponential, I find my initial value, which is usually given, and k, which I usually have to find. So it's 100 e raised to the negative 1155 times any time, and that will give me how many milligrams I have in my bloodstream t hours after I've taken this particular type of drug. Alright, so there's the equation that I'm going to have to use for the rest of the problem. So again, you have to be able to find the equation to do the rest of the problem. Alright, the next part of the problem is if the effect of the drug wears off when there's only 25 milligrams left, when will? Right? You no longer feel the effect of drug, meaning after how many hours will the effect wear off. So I'm looking for a time. Alright, I want to know the time when I only have 25 milligrams left, because when only 25 are left, I no longer feel the effects of the drug. Alright, so I'm looking for when my quantity, q of t, is down to 25 milligrams. Alright, and I want to solve for time. So I take my equation, that I found in the previous part, set it equal to 25 and solve for time. So again, solve like we've been doing before, isolate the e. And so on this side, I'm left with e to the, and I forgot my negative, negative 0.1155 times time equals 25 divided by 100, which I can write as a nice decimal, 2.25. Take the natural log, and so I get negative 1155 times time equals the natural log of 0.25. Divide by the k. Alright, so this is what you're going to plug into the calculator. You're going to plug in natural log of a quarter, 0.25, divided by that k. And you're going to get your time. And again, I'm going to round. So it comes out 12.00. So I'm going to round to 12. Alright, don't leave just 12. It's when will, which again is a time in hours. So 12 hours. So that's when you'll no longer feel the effects of the drug. Alright, just to point out what's going on here, right? If I decay down to 25 milligrams, that means I'm a quarter of what I started with. And so just kind of compare it to half-life. I'm looking for the time. I'll decay down to a quarter of what I started with. So I'm looking for the quarter time. And so it's similar to what we did before. It's the natural log of the quarter divided by k. It's kind of what I talked about in the last set of notes. So I can do this for anything. If I want to know what it takes to download down to a tenth of its size, it'd be the same thing. It'd be the natural log of a tenth divided by k. And that's kind of a nice feature of exponentials. Alright, so the answer to that one was 12 hours. Alright, so the last one, not the last one, we still have two more. Alright, so two more, and then we're done. Alright, so the next one, not the last one. Alright, how fast will the drug be decaying in the bloodstream after 2 hours? So now we're doing the calculus. Alright, how fast, which means I need my derivative. Alright, so I want to find my derivative at 2. So I need to find my original function, so I'm just going to write it down. If I remember, my original function was 100e to the negative 0.1155 times time. Alright, the derivative of that is what I'm looking for, and then I'm going to plug 2 into it. Alright, so the derivative. Alright, derivative of exponential is itself, so 100e to the 0.1155 times time, but I'm not done. Times the derivative of the inside, so it's going to be times that negative 0.1155. So it's always times k. The simple uninhibited exponential growth in Decay, that's always going to happen. All right, I'm going to clean it up. I'm going to multiply that out and move my decimal place over. So negative 11.55 e to the constant times time. All right, and now I'm going to plug my 2 in. Oh, I'm going to round a couple decimal places because it's milligrams. I can have a fraction of a milligram, right? So 9.17, which again is not my answer. I got to answer the question. How fast? All right, so the drug was decaying at a rate of 9.17 milligrams per hour. Alright, that's how fast, right? I'm answering the question. 2 hours after they've taken the drug, the body's breaking it down in the bloodstream at a speed of 9.17 milligrams per hour. Alright, so there's my answer. I answered the question and I provided units. Alright, now the last one. We're finding this is the last one on this set of notes. I know this is a long one. There were 4 problems we needed to get through. Alright, when will? What time, right? When will? We're looking for a time. The drug be decaying at a rate of 2.9 milligrams per hour. Alright, so this time we're given the rate. So we're given the derivative, right? The derivative is my rate. Right? We specifically want the rate to equal 2.9. Right? And what I have to remember about my 2.9 is it's decaying, right? I'm losing 2.9 milligrams per hour. So the speed is going down, and I've got to remember that negative, right, when it's a decaying case. And if you forget it, when you go to start solving this, you're going to eventually take a natural log, and we can't take a natural log of a negative number, and so you'll eventually remember because it'll give you an error when you're solving it. Alright, so I'm going to take my derivative, set it equal to negative 2.9. So negative 2.9, my rate of decay, equals my negative 11.55 e to that negative k times time. Solve for e, divide by the 11.55. And this is the step where you hopefully remember the negative if you've forgotten it, because I need this negative to cancel with this negative, because my next step is going to be taking a logarithm. So I'm just going to write the negative cancels out the negative, as we don't want to round this fraction, and it might come out nicely. You can plug it in your calculator and see if it does. I'm just going to leave it. I'm going to take the natural log of that fraction where the negatives canceled, natural log of the other side. And so I've got the natural log of 2.9 over 11.55 equals our k times time. All right, and divide by that k, negative 11.55. And again, you have to remember your negative here too. Time is positive. If time comes out negative, you've forgotten a negative somewhere. All right, again, if you can't plug the natural log in, you forgot your negative on the start. So this is what you're going to plug into the calculator. Natural log of the fraction, exactly without rounding, 2.9 divided by 11.55, end parentheses, divide by the k, which again is negative 0.1155. It's going to come out 11.965, which I might round that to 12. Alright, so 12. And again, don't leave it. When will. 12 what? 12 minutes, days, seconds, whatever. In this particular application, time is hours. So that's when it will happen. 12 hours. Alright, so we're going to wrap it up there. The next set of notes is going to look at a special type of this case called the continuously compounded interest, special type in again, finance. And so that's going to be the next video, and that one will be a much shorter one than this one. This one was a fairly long one. So make sure you go over it, understand what's going on. These are pretty straightforward, and students usually remember these from algebra, and the calculus isn't that bad because, again, it's usually just the e function times whatever the k came out to be. And so go look it over, and we'll wrap it up there.